lecture, I want to talk about some of the ideas which go under the name of double field theory, which started off with my work with Barton Zwieback, and I'll give, and there's been a lot of papers since, so I'll give some of the references towards the end. So let me remind you, I guess I need a longer stick. Is there a laser pointer or anything? So for strings on a torus, we've seen they're labelled by a momentum and a winding, and the string can be thought of as giving rise to an infinite set of fields. And as we'll argue, the fields, rather than just depending on momentum, P, will depend on the momentum plus the winding in the case of the strings on a torus. Whereas in flat space, in Minkowski space, they would just depend on the momentum. And then Fourier transforming gives an infinite set of fields on the doubled space. And the double field theory, and this gives rise to a double field theory from the closed string field theory, which consists of an infinite set of fields which, instead of just depending on x, will now depend on both x and x tilde. As I'll explain this, it's not quite a conventional field theory, that there's necessarily going to be some kind of non-locality in the double space, and I'll try and explain what that is. And a lot of the work has been focused on trying to look for a subsector of a finite set of fields, for example, a metric B field of Duotton, but where the dependence is now on twice the number of coordinates. So this would still be a d by d metric, but it would matrix, but it would now depend on 2D coordinates. And as we'll see, this will have a big effect on things like gauge invariances, and so to try and see what the analog of diffeomorphisms is on this context will be an interesting question. So I'll be looking at the double field theory as a field theory on the double torus, which I introduced yesterday. And the general solution of string theory will necessarily involve these double fields. So it means that string theory is not quite a conventional theory of the type we're used to, at least on a torus, but it's going to be something rather more exotic, something which is not captured by the supergravity theory. And one of the motivations, as I said, was to describe the kind of non-geometric backgrounds I talked about, introduced yesterday. Although I won't have time to talk about that in this talk, that's one of the main motivations and one of the directions in which I hope a lot of progress could be made in the future. But I want to stress is there's a real dependence on the full double geometry in this theory, that the dual dimensions are not auxiliary or a gauge artifact. And so the double geometry is both physical and dynamical. And I'll try and explain what I mean by that. So we know that in the conventional theory that there's diffeomorphisms of B-field gauge transformations. And what we'll see is in the double theory there's a novel symmetry which will reduce to that in certain cases when the fields, for example, are independent of x tilde. But will have to be something which was more general than that. We'll see that for background, as far as the interpretation goes, conventional backgrounds depending on x will be seen by particles, whereas dependence on x tilde will be seen by winding modes. And backgrounds which depend on both will be something less familiar and less easy to interpret. And what we'll see, what I'll try and argue is that this double field theory captures some of the exotic and complicated structure of the interacting string, which is hard to get at in other ways. And although some of these things are present in string field theory, the hope is that in looking for a small subset, will be given a finite subset of fields, will be able to analyze some of these things in a much simpler, in a more accessible context. One of the advantages is that the T-duality will be manifest, and also there'll be a generalization of T-duality. We saw yesterday that T-duality requires isometry. T-duality is introduced by Boucher as formulated in the Boucher rules. It requires isometries of the target space. And I'll be talking about the generalization of that, which arises in double field theory, in which no isometries are needed. And the work I'll be just talking about follows on from some very, very important early work in this direction from quite some time ago by Warren Siegel and Arkady Tseytlin, following rather different approaches. So let's talk about strings. We've talked a lot about strings on the torus, but let me introduce some notation for the purposes of this talk. This So we'll have a target space which is a product of an n-dimensional Minkowski space across a d-torus. And we'll choose coordinates xi, which will split it into x mu, which are the coordinates on the Minkowski space, and xa, which are coordinates on the torus. And then there are corresponding momenta, p mu and pa, and corresponding winding numbers, w, I, and dual coordinates x tilde. So for the compact dimensions, we have that the momentum and the winding numbers are discrete, as we talked about yesterday, as we talked about in previous lectures. The momentum is quantized, and the winding number is a discrete object. And so these are two integer-valued, in a suitable base of integer-valued vectors. They lie in a lattice known as the Narayan lattice. And Fourier transforming discrete variables gives rise to periodic coordinates. So Fourier transforming P gives a periodic xa, and Fourier transforming W gives a periodic x tilde. These are the coordinates on the double torus. In the non-compact dimensions, x and p are continuous in the usual way. And we'll usually take the winding in the non-compact directions to be 0. After all, as an infinite string in a non-compact direction would have infinite energy, and so would be, and so it's usual to take these to be 0. So this means that w equals 0 means that d by the x tilde is 0. So the fields will be independent of the double coordinate x tilde mu, which I introduced up there. So they only depend on x mu, but not x tilde mu. They depend on both of the double fields here. So why did I introduce x tilde mu? So that the notation is more compact, and I can deal with all coordinates at the same time without having to have different formulae for compact, non-compact, and mixed coordinates. And we'll choose to start with a constant background metric and B field, G and B, which are combined as before into a general matrix E. So as we saw yesterday, T-duality, as we discussed yesterday, T-duality exchanges momentum and winding. It gives rise to equivalence of string theories on dual background with very different geometries and topologies. And in the string field theory, which is going to be, which I'm not going to say too much about, I introduced it briefly in the first lecture, but I'll just use it as a motivation for some of the things I'll be describing, although in the work with Barton we use string field theory to derive a lot of the formulae which I'm going to talk about. And the string field theory gives rise to fields which depend on both x and x tilde, and that's necessary for, and with that dependence, then the string field theory is manifestly T-duality invariant, as was shown by some time ago by Huber and Stieback. So conventional T-duality works for fields which don't depend on the torus coordinates. In other words, there are isometries in the torus directions. They're independent of xa, and of course independent of x tilde a. So the Boucher rules are for fields which just depend on the base coordinates, which are here taken to be non-compact. And one of the aims is in the generalized T-duality is to look at the generalization of this for fields which depend on all of these coordinates, where there's no isometries and there's also dependence on this weird x tilde coordinate. And the idea that there should be such a duality was one of the things talked about in the paper that I had early on in the Teach-Dabelka. So what does string field theory give us? It gives it formulates strings in terms of a field phi on loop space. So x of sigma would be a loop in space-time, parameterized by a circular coordinate, a periodic coordinate sigma. And so phi, a functional of x of sigma, is a field which represents, which is associated with the probability of finding a string on the loop x of sigma. And it turns out, for technical reasons, it's extended not just to the space, but to a space with an extra ghost coordinate, c of sigma. But I won't focus on that today. And x of sigma has an expansion, as we had we saw it twisted in the first lecture, in terms of a centre of mass coordinate, momentum, and oscillators. And here here I'm looking just in Minkowski spaces, so for the moment there's no winding, and I'm going to put the winding in on the next transparency. And so the conventional story is one has, for the closed string field theory, one can expand the string field, and one expands in the oscillators, and one gets an infinite set of fields which still depend on the centre of mass coordinate x. And so one gets the familiar metric B field and dilaton, and then an infinite set of massive fields, which can have arbitrarily many indices and have complicated tensor structures. So there's an infinite tower of massive fields which come along with the massless ones. And in the bosonic string there's also a tachyon which starts here. Then integrating out the massive fields can give an effective field theory for the massless fields. And integrating out the massive fields is this, one finds an effective action which starts off as a familiar Einstein-Hilbert term for the metric, and then the conventional kinetic term for B and phi, so one gets the photonic part of the supergravity action. And then there are systematic higher derivative corrections involving higher powers of curvature which arise at higher orders in alpha prime. So that's a lightning review of the standard story which arises on Minkowski space. So what changes if we now go to a torus? So it's a very similar story, but what changes is that now expanding the coordinate now gives x of sigma, now gives dependence on the winding modes or the conjugate x tilde coordinates. And so expanding in the oscillators, we now get an infinite set of double fields which depend on x and x tilde instead of just on x. And the index structure which arises from expanding out in the oscillator is exactly the same as it was in Minkowski space, but all that's changed is the dependence on the double fields. And one of the things we aim to do is try and find an effective field theory for a finite subset, for example, the ones which arose in the so-called massless limit. So let's talk a little bit. So what I want to do now is talk a little bit about the free field equations and how these things get together. So I talked about the kinematics and about how these fields arise. And in string theory, one gets field equations which come from the Virasoro constraints. One gets from L plus L0 equals 2, so 2 is the intercept, and the value of the intercept will depend on whether we're talking about the superstring or the bosonic string. For the purposes of this slide, I'm giving the results for the bosonic string. Then one has a mass condition which is that p squared plus w squared. So remember, p includes the momentum in both the compact and the non-compact directions, whereas the w involves just the winding in the compact directions, and assuming that w is 0 in the non-compact directions. And each state is so the oscillators, each of them defines a Fock space, and so there's a number operator for the oscillators which arise, and so there's a number operator for the left-moving oscillators, which is n, and one for the right-moving oscillators, which is n bar. And so there's the mass depends on these number operators, so that you get massless fields at n equals n bar equals 1, and then for higher n one gets massive fields. And then in addition there's another equation which is related to the constraint of invariance under reparameterizations of sigma, which is the L minus L0 bar equals 0. And this is usually often sometimes called the level matching condition, because in the absence of winding, we say that n equals n bar. But in the presence of winding, there's an interesting and strange mixed term which involves p dot w, and that will have an important role to play in what we're going to talk about. So the first equation we treat as a field equation and gives rise to a kinetic operator in the double space. So Fourier transforming p squared plus w squared, we get a Laplacian which involves both x and x tilde. And so for the double fields, we'll satisfy this a field equation which involves a Laplacian in this double space. And then there's this other equation in the string field theory we'll treat as a constraint. And we're doing that because that's what happens in string field theory. And although it would seem desirable to find a way of formulating the theory in which we treat both in the same footing. No consistent way has been found of doing that. And so we have this slightly strange situation where we treat one as a constraint and one as a field equation. So if we Fourier transform P.W, we get d2 by dx by dx and dx tilde. So we get a constraint that delta minus a constant equals, well, each field equals 0, where this mu depends on n minus n bar. And for states which have got matching levels, we'll get this mu where n equals n bar, this will be, which will be the fields we'll be talking about, this mu is 0. So this kinetic operator involves a kinetic, could be thought of as a Laplacian associated with this metric, whereas this one can be thought of as a Laplacian with respect to this indefinite metric that's got signature d comma d. So if we look at the fields which have got n equals n bar equals 1, the bosonic string, they consist of just these three fields, and they'll satisfy these equations, and so I'll refer to these as double massless. So they're massless with respect to the operator p squared plus w squared, where again I remind you that includes both compact and non-compact directions. So how should we think about these constraints? So if we look at the constrained fields, it's useful to go to momentum space where we have a psi which depends on these p's and just the compact w's. And so the delta is p dot w. And so the constraint that delta minus a constant equals 0 gives either a cone if the constant is 0 or a hyperboloid if it's not. And so we're starting off in dimension in momentum space n plus 2d, n compact, non-compact directions and d plus d compact ones. And so this gives a hypersurface in that of one dimension less, the cone or the hyperboloid. So double field theory talks about fields on the cone or hyperboloid in which p and w are discrete for the compact directions. And so that gives us a picture of what's going on. But one of the problems is that the naive product of fields which lie on the cone or the hyperboloid will not lie on the cone or hyperboloid. So that means that one can't use naive products of fields in writing down vertices and interactions. But one will need explicit projectors to multiply two fields and then must project down onto the cone. There's a small subset of the fields which depend on just d of the 2d torus momenta. For example, fields which just depend on p mu and pa, or just p mu and wa. So if one restricts to a set of fields like this, the product of two fields that just depend on the p's will also just depend on the p's. And these are clearly killed by p of w equals 0, because w is 0. So the product of such fields which depend on just half of the compact directions will close amongst themselves when you multiply them, and no projectors will be needed. So if we restrict ourselves to fields which depend on just n plus d of the coordinates or the momenta, then we could get a set of fields which close amongst themselves, and we can treat them consistently as giving a closed sector. There's a simple subsector with no projectors needed and no cocycles. But I want to stress that the full double field theory involves the stuff up here, which involves many dependence on both momentum and winding at the same time. And restricting down here gives us a subset where we could treat as a conventional field theory. In fact, because this case, because it just depends on p, mu, and pa, it's a rewriting of the usual field theory for these things, because they just depend on the p's, or correspondingly on the x's and not the x tildes. And this case would be related to that one by a t-duality which swaps the pa with the wa. So in some sense, these are a kind of a trivial subsector, which is the subsector where one can make most progress. And in fact, most of the papers on double field theory is talking about these kinds of restricted fields. Whereas what the really novel stuff will be in trying to understand this stuff up here. So what does this theory look like? So let's look at a torus background. So we've got introduced a background metric GAB and VAB on the torus, and Minkowski metric in the non-compact directions. And for simplicity in this talk, I'll take the background Bij to be 0, but it can easily be incorporated. It just makes the formulae a bit more complicated. So just to keep the notation simple, I'm going to look at that. I'm going to look at fluctuations Hij about the metric, the background metric, and fluctuations Bij about the background B field, which is 0. And I'll consider arbitrary fluctuations in all of the parts of the metric and B field, and they'll combine those into a tensor little e, which has got whose symmetric part is the metric fluctuation, and the symmetric part is the B field fluctuation. And I'll define this derivative partial tilde as being where the index is lowered with the background metric. So the usual action for the metric and B field with no dependence on x tilde is the familiar action of the Einstein-Hilbert term plus kinetic terms for the dilaton and H. And be useful to, so if we expand this out in fluctuations around the background, there'll be a piece which is quadratic in the fluctuations, and let me call the Lagrangian for that L. And that will depend on the background fields, but it also will depend quadratically on the metric, the B field, and the dilaton, and will just depend on the usual derivatives. And rather than use the dilaton, I'll introduce the variable I talked about yesterday, this d, which is related by this redefinition. And I remind you that the point of this was that this e to the minus 2d was invariant under the Boucher rules. The shift in the dilaton, the conventional dilaton, is compensated by the shift by the transformation of the root det g. So the double field theory action can be written in terms of this Lagrangian, and it's got the first term is, so it's an integral over both x and x tilde. The first term is exactly this term we had from the last slide, but now integrated over x tilde as well. The second term is now the thing which is related to this by a linearized t-duality transformation, which involves splitting the signs of h and b and leaving d invariant as it should be, and also swapping the derivative with respect to x to a derivative with respect to x tilde. So the first two terms are pretty much what one might have expected. And then there's a first surprise, which is that there's some strange mixed terms which involve mixing between the metric and the B field, and between the two kinds of, between the normal derivatives and the dual derivatives. So this can be thought of as being the action plus the dual action, plus some strange mixing terms which perhaps were unexpected, but it needs for the gauge invariance. And the action is invariant under some interesting gauge transformations. So one has transformations of the metric, the B field, and the dilaton of this form. So first of all, let's suppose that that the parameters epsilon and epsilon tilde are independent of x tilde. So that would mean that this term and that term would vanish. Then this epsilon term for the h would just be the linearized diffeomorphism transformations, and epsilon would be seen as the parameter of diffeomorphisms. And then this term here would be the usual antisymmetric tensor gauge transformation with parameter epsilon tilde. So, but now if we look at parameters which are dependent on x tilde, then this term and this term would drop out. This term up here would be would look like linearized diffeomorphisms, but now in the dual x tilde directions. And this term here would look like antisymmetric tensor gauge transformations, but again in the dual directions. And so we find that in these formulae, the diffeomorphisms and B-field transformations are mixed together, and they appear in a surprisingly symmetrical way, which is was rather pleasing. And I should stress that the constraint that the fields are annihilated by d dot d tilde is crucial in showing the invariance of the action under these transformations, that the parameters in the field satisfy this constraint is used in showing this linearized invariance. So this is the quadratic form of the action. So now we can use this to try and look for, trying to use Noether methods to try and find the cubic action, the next terms, trying to add interactions and trying to look for the next terms in that. This was done in the first paper with Barton Seeback, where he found the full cubic action and the, so the full action to cubic order in the fields, and with corresponding modifications to the gauge transformation to linear order in the fields. So this is working for the full double field theory without any constraints, without any restricting to the field. So they depend on the full set of fields living on the cone rather than restricting to restricted fields, which depend on a much smaller subspace. And the background, so we can now talk about T-duality transformations in this theory. So the background transformations are precisely transforming by the Boucher rules, with E transforming by the fractional linear transformations we saw before, and little d, the dilaton, not transforming at all. And here, the matrix A, B, C, D are the D by D blocks of the matrix in ODDZ. And X and X tilde transform as a vector under these transformations. Indeed, that was one of the motivations for introducing X tilde, to give something that's transformed linearly. And the double field theory action has a T-duality symmetry. To specify how that works, we need to say how the fluctuation fields transform under these transformations. So it turns out that after a lot of work, one finds that the transformations of E and the fluctuations are as shown here. So little d, now it depends on X and X tilde, instead of being invariant under the toroidal coordinates. So now we're dropping the condition of isometrism, and we find that it transforms in the perhaps the simplest way it might do, which is transforming to a scalar. So X transforms, and there's a transformation which mixes the toroidal coordinate little x with the winding coordinate little x tilde. And whereas the non-compact directions don't transform at all under the T-dualities. We're just looking at T-dualities which act on the compact directions. So this is just saying that although it's not invariant, it transforms as a scalar. And this fluctuation, little e, has some interesting transformations which involve a tensorial type transformation where it involves the matrix M, where this M is defined in this way, as D by D matrices. And these transformations leave the theory invariant with general momentum and winding dependence. So this is the kind of generalized T-duality transformation I was advertising earlier. So now I need to say something about these tricky points to do with the projectors and cocycles. I mentioned that the naive product of fields which satisfy the constraint won't satisfy the constraint. If you have two fields which are killed by delta, then their product won't be. And similarly, the two fields which is annihilated by L0 minus L0 bar, which I'm abbreviating to L0 minus, will not satisfy the constraint. So what that means is in the string field theory is an explicit projection which is needed in the interactions, which involves a projection onto the cone with L0 minus. And that has some dramatic features. It leads to a very strange kind of symmetry, which is not on the symmetry algebra is not on the algebra, but something more general called a homotopy algebra. I won't have time to say anything about that today, but it's a very interesting algebraic structure. And it seems that a very similar thing is needed here in the context of the double field theory. And it indeed will inherit those from string field theory. So the double field theory interactions will require some projections. And there's also an issue with cocycles, which is something which I will now try and explain a bit better. So the first lecture we talked about T-duality, and I showed that it's a symmetry of the free spectrum. There's a question which arises, which I postponed, which is the question about whether or not T-duality is a symmetry of the interactions. This is a point which is often glossed over, and it turns out the answer is a little more subtle than people usually give credit for. And this subtlety turns out to be important in what I'm going to talk about. So let me try and explain concisely what's going on here. So let me, for simplicity, work at the self-dual radius, where the radius of the circle is root alpha prime, and I'll look at just one circle. So the left and right moving momenta are n minus w and n plus w in units in which alpha prime is 1. And so the naive T-duality, which I'll call T0, is the one we discussed before, which xl goes to minus xl, and x right goes to x right. So when you expand out the left and right moving parts of x, it has the effect of swapping momentum and winding number. So n and w are integers here, so w is what I called m before. And the other thing is that one acts with -1 times the left-handed number operator. In other words, one takes each left-handed oscillator and multiplies it by -1. So there's a net effect of acting with -1 to the n hat left. So if we look at the quantum T-duality, it's a question about how it will act on a state. So it will act by swapping momentum n and w to w and n. So the states are labelled by n and w, plus the number operators for each of the different oscillators. So I'm using the notation little I here to represent the infinite set of oscillators which arise. And then acting on this with the total left-handed number operator to the minus 1 to the power of the left-handed number operator. So one has the action on a state which follows from the naive T-duality. But the quantum theory representation, there's a possibility of introducing a phase up here, So in the quantum T-duality, there's a possibility of introducing a phase, which provided this satisfies this constraint. So the quantum T-duality can be T0 plus a phase to give some kind of projective representation. So we can now turn to the question about whether the vertex operators are invariant under T-duality. So the vertex operators all involve this kind of structure with some p left e to the I p left dot x left plus I times p right dot x right. And one of the problems with these operators is, so this would be the vertex operator for a tachyon. If it was for various tensor fields, there'd be very extra structure involving the oscillators added onto this, or derivatives of the field, of the x's. The trouble with these operators is they're not mutually local, and that's to do with the fact that momentum and winding are not mutually local. So if one carefully calculates the equal time commutation relations between two such operators at places like separated at position sigma 1 and sigma 2, one finds that they don't commute. There's this extra factor involving the momentum dot winding, which would drop out if the winding was 0. So this is an interesting calculation. So this is the details of this could all be seen in Polchinski, where he works out these commutation relations and these vertex and these cocycles. And so this means that bosonic operators will sometimes commute and sometimes anti-commute. So you get e to the pi I times an integer, so the extra factor is either +1 or -1, depending on these between the momentum on the cross products between n and w prime and w and n primes. One can define new operators, which are the naive operators multiplied by something known as a cocycle, which are mutually local. And this operator is not uniquely defined. It can be chosen to be this, for example. So n hat is the operator whose eigenvalue is the momentum little n, the integer part of the momentum little n, and w is an n are the values of n and w occurring here. So this is an operator where this n hat will act on whatever field's occurring here and work and will take the value of the eigenvalue of n occurring over here. And once one has these improved vertex operators, which are needed to get bosonic operators, so before sometimes they commuted and sometimes they anti-commuted depending on n and w. Now these all commute and they're all mutually local when space-light separated, as they should be. But now, if one looks at the operator product expansion of these fields, the presence of these cocycles means that the naive action of T0 doesn't preserve the OPEs. And there's a property duality which does preserve these OPEs, which is given by T0 plus a phase. And this phase is given by the action of -1 to the n hat w hat, where the n hat is the, and the w hat are the operators whose eigenvalues are n and w. So this is the momentum and winding number operators. And so what this means is that the naive, so that when acting on, with T-duality on vertex operators and on the interactions, it's not the naive T-duality, but there's this extra factors which arise here. And so this means that when one's writing down the string vertices, or the interacting terms in the string theory, they're necessarily not the naive vertices, but ones involving some extra funny signs, depending on momentum and winding, or in position space x and x tilde. And these are strings sort of mildly non-local factors. And the fact that these arise in the string theories implies that such factors must also arise in the double field theory. At least if one looks at the full double field theory and not just a restricted sector. But if one looks at the restricted sector where things are independent of n or of w, then these factors would drop out and then things would become much simpler. But there's this interesting fact that, that the way T-duality works in the interactions is perhaps not the simple way in which it's often presented, and that is often supposed. And these signs are important in various applications. And the string field theory interactions, for example, all have necessarily such cocycles. So there's these awkward situation, this awkward structure which involves both cocycles and projectors. So, but as I argued, these would drop out if I looked at the restricted fields. And so that's what I'm going to do for the rest of this lecture. I was going to focus on fields which just depend on half of the coordinates. For example, fields which depend on just the space-time coordinates x, or on fields which are related to that by T-duality. Then for such a restricted subsector, which is then the product of fields will necessarily satisfy the condition, will again be restricted in this way. We can formulate the theory in a way which is T-duality covariant, which is in a way which is independent of which half of the coordinates we're taking the fields to depend on. So that T-duality will act as to change which half of the coordinates it would depend on. But really in doing this, we're really just restricting ourselves to a duality covariant rewriting of the conventional theory rather than looking at something intrinsically more complicated for the full double field theory. But with the restricted fields, we can go a long way to find the structure of the theory to all orders. So let me now look at such restricted double field theory. So restricting the fields to some d-dimensional subspace, and which subspace is rotated from one space to another by T-duality. So we have a background field capital E and a fluctuation little e. And it turns out there's a nonlinear relation, there's a field which is background independent, is given by E plus, so little e is a matrix, so this is, I'm using matrix notation here. So this curling E has got nonlinear dependence on these little e's. But it turns out that this combination, for reasons I don't have time to go into, turns out to be the covariant background independent object, and whose symmetric and antisymmetric parts define the full metric and the full B field. And so this relation is essentially the relation which tells you how the fields, little e, which arise in string field theory, are related to the conventional supergravity fields, which are curly or little g and little b. So it's useful to use a covariant notation where we combine all the coordinates together into double coordinates and double derivatives. There should be a tilde on this partial here, sorry about that. And we should use an ODD invariant metric, which we'll call eta, which has got signature d comma d. So it turns out that we find that the T-duality transformations are now very simple in this form. These transformations are ones whose rewritten in terms of the fluctuations Lipperle gives the filming I had before. But now we see that they fit together into a very nice approach. So these are the fractional linear transformations one might have expected, but with the difference that now we have x here and x prime here. And here we have d transforming as a scalar as before. So in the case when the fields are independent of the toroidal coordinates and their corresponding winding coordinates, then we get these reduced to precisely the Boucher rules we had yesterday. But in the more general case, it gives a generalization to the case without isometries. So maybe I'll skip this one, just a couple of things I wanted to cover. So if we, the theory could be rewritten in terms of a generalized metric. So this is a metric on the double space, which is made up from the little g and little b in this strange way. So there are two metrics on the double space. There's eta mn, which has got signature, which is a constant, that's got signature d comma d. And there's this other metric h. If little g were positive definite, this would be a positive definite metric. And if little g was Lorentzian signature, then curly h would be double Lorentzian signature. In other words, there'd be 2d minus 1, 2 times d minus 1 space-like directions and 2 time-like directions. And these satisfy a constraint that if we define, so we've got two metrics, so let me choose to raise and lower the metrics with the constant metric, the indices of the constant metric eta. So we define h with indices upstairs as the thing raised with eta. And the constraint is saying that curly h is, with the upstairs indices, is the inverse of the curly h with the downstairs indices. So this constraint in fact is what's needed to imply that h isn't a general symmetric matrix with 2d by 2d entries, but is one whose general form is the matrix given at the top, parameterized by little g and little b. So if I define the matrix S, which is eta inverse times curly h, then S squared is eta inverse h, eta inverse times h. So this is just the thing which is where the two indices are raised by the etas. So this is just h inverse, sort of the constraint, times h, which is 1. And so this curly h is this S, which is made up of the two metrics, and something which squares to plus 1. And this is the S which I used yesterday in the formulation of the double sigma model, the constraint there, which gives something squared to plus 1. Now, the beauty of this curly h is it now transforms covariantly under the ODD transformation. So whereas the curly E, which was a d by d matrix, transformed under with fractional linear transformations, this curly H transforms linearly under the transformation. So if H is a matrix in 2D in ODD, then this H prime transforms as a tensor under ODD in this way. So you've got this matrix acting on the indices, but also acting to transform X to X prime in this way. So now that things are looking kind of tensorial, that simplifies things a great deal. And the full nonlinear action can be written in a very nice way. It can be written in terms of curly H and D, and it just has a few simple terms. It involves its two derivatives, of course. The derivatives involve, these are double derivatives, so they both involve derivatives with respect to X and derivatives with respect to X tilde. And this has a remarkable feature that, so remember that H with the indices upstairs is just things raised, just the indices raised with the background metric, the constant nature metric eta. So we see that this equation is cubic in the metric curly H. So remarkably, we find an action which is cubic, or the Lagrangian which is cubic, and then multiplied by the measure factor e to the minus 2d. And so that's what I just said. And the gauge transformations are rather interesting. They can be written in a simple form where H transforms in this way. And in showing the invariance of this action, one needs to use the constraints. But since we're dealing with restricted fields, the constraints are automatically satisfied. And this transformation can be rewritten as something which I'll call a generalized Lie derivative. And what I'm going to do in the next slides is try and talk about what that means. So this looks a bit like a Lie derivative, but there's some extra terms. A normal Lie derivative for diffeomorphisms in the double space would involve three terms, which would be the first one, and then plus this one, plus this one. So you've got two strange extra terms which is coming in here, which is a bit of a surprise. So what does that mean? So we can define a generalized Lie derivative in this kind with arbitrary numbers of upstairs and downstairs indices. So here written a tensor with one up and one down, just to show how it goes. So we've got two kinds of structures, one acting on the upper index and one on the lower index. And then one can use the tensorial property to extend this to arbitrary numbers of indices. So this can be written as a term which is the normal Lie derivative plus two extra terms, and the two extra terms have got the indices in funny positions, and that's because there's some hidden etas used to raise and lower indices. So we get normal Lie derivative plus some terms which depend explicitly on the background metric eta, on this constant metric eta. And so what's allowing us to have this kind of generalization is the fact that we're dealing with space with two metrics, one of which is dynamical, but the other one is kind of kinematic, this eta. We can write down, use a generalized curvature scalar. This is something which is related by up to total derivatives by the Lagrangian we had before, which has the property that the action could be written up to total derivatives as this. And so the gauge symmetry could be understood in the fact that R transforms as a scalar under these transformations. So here there's no indices on the R, so the generalized Lie derivative just gives the conventional thing. And this e to the minus 2d turns out to transform as a density under these transformations. And so with these transformations, we find that the action is invariant. So we have a two-derivative action which could be written in terms of terms which involve two normal derivatives, two dual derivatives, and mixed terms. So if we look at the first term, S0, which is the usual action could be rewritten in terms of the usual fields, and then up to total derivatives, it gives precisely the conventional action. So if we could write S0 as being this action, we get this conventional action arising. S2 turns out to be what one would expect for the T dual of that, with E replaced by E inverse, and the normal derivative replaced by the dual one. And the S1 contains the nonlinear version of the strange mixed terms we had before, which are needed for gauge invariance. So we've looked at the restricted double field theory, where the fields are independent of half of the coordinates. If they're independent of x tilde, then it's equivalent to the usual action, as we've just seen that explicitly. It's related by field definitions and plus total derivatives to the usual action. But it has the property of being duality covariant, and that the duality changes which half of the coordinates the theory is independent of. It's been shown that this is equivalent to an earlier version of the fork theory from Warren Siegel, and it has the advantage that it's hopefully useful for non-geometric backgrounds. But let me say a little bit more about the gauge algebra and the Lie derivatives. So, if we could combine the parameters into epsilon and epsilon tilde, we called epsilon and epsilon tilde before into this 2D vector sigma m, and the gauge algebra could be written in terms of what I might call the C bracket, which is the thing given by the commutator of these Lie derivatives. And this turns out to be have a very nice form. We get the conventional Lie bracket as if these were diffeomorphisms in the higher limit of the double space, plus an extra term depending explicitly on these spaces. So remember that the parameters are restricted to some subspace M, depending on half of the coordinates. And so with respect to this subspace, we can split these into a vector plus a 1 form, and rotating which the space M would change which half of vectors and which half of 1 forms. And when one restricts it to vectors plus 1 forms, we recover what is a bracket which is familiar in some of the mathematics literature, known as the Courant bracket on this space. So what we're getting is a covariant way of writing the Courant bracket, which arises in this way. And the same covariant form of this algebra, with precisely the same C bracket, was found earlier in the work by Warren Siegel.
Chris, sorry, in this expression you have for the C bracket.
Yeah.
Second term, there is the excess of index, I think.
Yes, sigma 1 and sigma 2 should have indices, M and N. Yes.
Yeah, so here this bracket has got a free index M, which I should, sorry, it should be an M, not an M on those, so there's a free index. So
yeah.
the bracket of 2 vectors will give another vector. Sorry, you're quite right, sorry.
So there is an M on the...
Yeah, so the upper M on the brackets and an upper M on those, and then I think everything balances.
Yeah, now it should be.
Yeah. So sorry about that, yeah. So in the case without the eta term, so this should be the usual Lie bracket, which takes 2 vectors and makes another vector. So one of the strange things which happens here is the Jacobian identities are not satisfied by this C bracket. So if we look at the nested brackets and take cyclic combinations, we find it's something which is non-zero. So the question arises as to how this bracket can be realized as a symmetry algebra. And the answer turns out to be related to the fact that symmetry is reducible. The parameters which are of the form eta inverse derivative of the scalar don't act. So this is related to the fact that for a 2-form gauge field, the gauge transformation delta B equals d alpha. If alpha itself is exact, then the transformation doesn't act, and the delta B is 0. So sigmas of this kind don't act to give a transformation which is 0. And so the resolution is that although the Jacobiator, the thing which you get from taking the nested products and cycling, is non-zero, it gives something which is does not act on the field. So that the failure of the Jacobian identities gives a transformation which doesn't act on the fields, and so it gives a way in which this symmetry can be realized. And the Lie bracket can be used, the Lie derivative can be used to define another kind of bracket, which is not quite the C bracket, but differs from it by a total derivative term. And so this gives a bracket which is no longer skew symmetric. But now this does satisfy a Jacobi-like identity. And this, when we restrict to the subspace, gives another kind of bracket which arises in the mathematics literature known as the Dorfman bracket. And it gives rise to a generalized Lie derivative which occurred earlier in the work of Granier, Nazian, Petrini, and Waldron. So my time's up, so let me just conclude. What I've tried to show is, I've tried to introduce some of the ideas related to double field theory. I've shown how to construct a cubic action. Sorry, we would construct a cubic action. I've shown you the quadratic part of that for the full double field theory. But the quartic part of this necessarily has new stringy features which involve these co-cycles and projectors which I talked about earlier. It has a T-duality symmetry, and the fact that the symmetry is not a conventional Lie algebra but is something more general is related to the fact that we saw that the Jacobi identities may be satisfied for the symmetry transformations we looked at. But nonetheless, there's some interesting way in which the theory managed to get around the fact that the naive Jacobi identities are not satisfied. And that's what gives something which is more general than the algebra structure. We've looked at the restricted double field theory, where we've been able to construct a nonlinear background, the nonlinear background independent theory, which is duality covariant, and saw that the gauge algebra gave rise to some interesting mathematical structures. So one of the motivations is trying to look for this is to try and look at the issues, stringy issues in a simpler setting than string field theory. And it would be very interesting to see what comes from that. In particular, the kind of mild non-locality which arises from the projectors and the co-cycles is rather interesting, and it would be very interesting to try and understand that better. There's been some recent work looking at the geometry of these theories. Nonetheless, it still seems as if there's more to understand as to what's going on there. In particular, the work of Waldron et al. Has looked at the geometry in relation to some of the kinds of connections which arose in the work of Gualtieri. But I still think there's more to be understood there. One of the key features has been we've been looking at spaces which are tori, or at least topologically products of tori and flat space, or more generally, in some cases, to toroidal spaces with toroidal fibrations. And that's related to the fact that we understand duality transformations in the case where there's tori or Calabi-Yau or very other special cases, but not in more general cases. And so we get a lot of structure which seems very specific to tori, and it seems very hard to imagine how this might generalize to other spaces. I mean, is this doubling something which is very specific to tori, or is it just a hint of some other kinds of features which might arise? And trying to understand that would be, I think, would be very interesting. But nonetheless, we've been able to make a lot of progress in just understanding the theory of the torus, which I think is very interesting and very suggestive. We've found the full theory with the restriction, but it would be very interesting to understand in more detail what the full theory would look like without the restriction. And there's issues as to whether one can really construct a full action for just these fields without. So there's clearly going to be a full theory depending on an infinite number of fields. But there's issues as to whether one can consistently integrate out all but a finite subset of the kind we looked at to find a consistent action which for just those fields. It's already quite dramatic that that works at the cubic level. It didn't need to. Things could have already gone wrong at that level, and we've checked explicitly that doesn't happen. But I wanted to stress finally that the double geometry is both physical and dynamical. We saw, looking at the three fields, or fields which depending on both x and x tilde, in which we got the dynamics generated by a Laplacian in the full doubled space, together with a constraint which was a we thought of as another Laplacian for a metric with signature d, d. So we've got two different metrics which arise, the generalized metric and the ODE invariant metric. And we have two Laplacians acting on these fields. But it's clear with just two field equations, one still can have non-trivial dependence on x, both x and x tilde, which involves many more than half, which depend on many more than just half of those coordinates. So that's the reason for saying that this double geometry gives rise to more general solutions, which will be both physical and dynamical, more general solutions which have non-trivial and real dependence on much more than half of the coordinates, so that the double geometry is both physical and dynamical. We've seen equations which tell us that the double geometry itself evolves and is dynamical, satisfying various field equations. So I'll conclude there. I've tried to, in these three lectures, I've tried to first of all introduce T-duality and I've also tried to talk about some of the aspects of T-duality which are often left out in various in pedagogical treatments and lectures. There's strange features involving, for example, the dilaton and the cocycles which arise there. I've then gone on to talk about how this affects the geometry, how it gives rise to non-geometric backgrounds, where one uses the symmetry as this enlarged symmetry to patch together physics in different coordinate patches to get what you call a class of non-geometric backgrounds. There are more classes of non-geometric backgrounds than the ones which I've just described. For example, taking more T-dualities of some T-folds will give some things which are not even locally geometric. And I haven't had time to talk about those. And today I've introduced the double geometry, which seems to be the way string theory wants to try and describe the physics associated with these, and to try and the kind of formulation which would be necessary and hopefully provide some insights into how string theory really works with these, in going beyond the familiar geometry of supergravity to give something more exotic and more general. So this is just the beginning. There's a lot more which needs to be done in understanding all this, but I hope I've given an introduction to, I aim to give an introduction to some of these ideas. And finally, here's a list of references to some more recent work. And in fact, in the last 2 days, there's a couple of papers on looking at the supersymmetric double field theory, which I haven't even had time to add to the slide, let alone to read, so I'm not in a position to comment on those. But here's a list of some of the related work which is going on in this area. So I'll stop there. Thank you.
Have you some preliminary hints to avoid ghosts from this picture, or they don't appear here?
Okay, good. So there's lots of generalizations involving extending to other string theories to include supersymmetry and so on. And as far as the restricted kinds of double field theory, there's already a lot of work, a lot of papers coming out of that, and there's a lot of things being done on that. There's very little been done so far, apart from the original work with Barton, where we're looking at the unrestricted double field theory. And so that's, I think, one of the key questions. Is for it really to be useful and to give something really new, it'd be good. I think it's important that progress is made in that direction. And the other kind of direction is the one I've also advertised, one of the motivations, is trying to understand what this says about non-geometric backgrounds and so on. So some of this we've heard about based on this paper in the talk yesterday, some related aspects about what the geometry of some of these non-geometric backgrounds, trying to understand some of the